Hello guys, welcome back to ptet.chemistry channel. So in this tutorial video, we'll continue these lecture tutorials on relative masses of atoms and molecules. These are very important. Just prior to us doing the concept on mole and stoichiometry, we really need to understand the idea of these relative masses. We already talked a little bit about relative atomic mass as well as relative molecular mass previously, and it's just basically about using these relative masses of atoms and molecules to work out molecular formula and empirical formula. As you could see, that you are expected as candidates or as students calculating the empirical formula and molecular formula. So this is part of the 5070 pure chemistry course, and this is also similar to any O-level or IGCSE chemistry, which is equivalent to any 14 to 16 years old chemistry curriculum all around the world. So here you should be able to define molecular formula. Simply means the actual number and the type of different atoms in one single molecule. This is the key bit of the definition actually. So to have molecular formula, you must be a simple covalent molecule. You cannot have molecular formula if you are not simple molecular. Okay, cannot, well, must be simple covalent molecular, meaning it must have simple molecular or simple covalent structure, because if you have a giant molecular or giant covalent structure, you can never exist as one single molecule, and therefore you cannot have molecular formula because of the definition. That is why when a question asks you molecular formula, or they tell you the molecular formula of blah 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 is blah blah blah, it means that you're looking at a simple molecular or simple covalent structure. Because it's a simple structure, it has low melting and boiling points. So there's a definition of molecular formula. Empirical formula, on the other hand, is to do with the simplest whole number ratio. So it has to be the simplest whole number ratio. It cannot have any other number other than whole number. And these are ratio of the different atoms or the ions in a compound. Okay, so most textbook will probably just say atoms, but then we also have empirical formula of ionic compound. So back at the start of this topic, couple of lecture tutorials ago, you were trying to balance out the charges on the ions. That was when we did the lowest common multiple, or you can think of it as the crisscross method, when you want to get the formula of an ionic compound starting from the ions. That was basically the idea of empirical formula, which is to do with the simplest whole number ratio of the different ions in ionic compound. But you could of course also have molecule as a compound, meaning simple molecules, and therefore we're looking at different simplest whole number ratio of different atoms instead. Okay, so that definition actually covers for different kind of compound, whether you have ionic compound which consists of ions, or you can have covalent compound which consists of atoms. But what is different between molecular and empirical is that they say in a compound, they don't say in one or in a molecule, because this thing only exists for simple molecular structure. Compound can be giant molecular compound, meaning things like carbon graphite, carbon diamond, which has infinite number of carbon atoms within the giant molecular structure. But the empirical formula of graphite and diamond, we write just carbon solid, just like that. We don't write infinity at all, because there's the simplest ratio of carbon atoms in the whole, well, in fact it's the element, isn't it? It's not even a compound. Okay, but then when you have silicon dioxide, so you know this is a giant molecular structure. It's got silicon bonded to 4 oxygen like this, and then each oxygen is bonded to 4 silicon. Each oxygen is bonded to 2 silicon. So each oxygen is bonded to 2 silicon, 2 silicon, 2 silicon. Each oxygen is bonded to 2 silicon, and each silicon in return form 4 covalent bond. 1, 2, 3, 4. Silicon is in group 4, 4 outer shell electrons. I hope that makes sense to you. Okay, so definition of molecular empirical formula are just like what usually questions started out with, and it's something that even the lower scoring candidate would be able, well, should be able to do. because by understanding definitions, you'll be able to do the next part, which is the calculation correctly, because this is to do with one single molecule. This is to do with the simplest whole number ratio of atoms or ions in a compound. So what are the steps to follow to calculate empirical formula? So there's this formula here which we haven't exactly covered yet because it's to do with mole concept, but you do need it in order to calculate empirical formula. So I'll just introduce it at this point. So N there refers to mole. If I just rub out this carbon solid and silicon dioxide, then I can write on it. N there refers to mole. So this is a quantity. It's just a way of quantifying stuff in chemistry. So it has a pronunciation of mole. The unit, typically a lot of books, a lot of teachers, a lot of students can just abbreviate it as M or L. Okay, and then it's equal to mass over relative atomic mass. So mass there is not in kilogram, the mass is in gram. That is very, very important. The mass is in gram, meaning G. So as you know, 1 kilogram is equal to 1000 gram. Okay, so it has to be in gram, not kilogram. Relative atomic mass. Relative atomic mass was just covered in the last lecture tutorial on, well, it was defined. If I just go back very, very quickly, but it's something stated in the syllabus. Candidates should be able to define it completely with all of these. Alright, so basically your periodic table shows you relative atomic mass. They are even kind enough to actually tell you in the periodic table that it's not mass number, it's not nucleon number, it's relative atomic mass, which is different from nucleon or mass number. These are international standard, as we did a couple of months ago as part of atomic structure. This is periodic table as given to you in the real exam. Going back to molecular and empirical formula. So these are just a couple of steps to do all of these. I'm not going to, read through each and every one of it, but just to highlight the concept of relative atomic mass, it has a unit of gram per mole. Okay, so we're going to show you a little bit of maths. If you have gram, mass in gram, divided by gram per mole. So what does this mean? This means gram times mole over gram. Because if you have gram divided by gram over mole, that is equal to this, or this is equal to this. When you have divide, you reciprocate it, you swap them around, and you become multiply. And I hope you can see the units of mass and mass cancel, well, gram and gram cancel, and you'll be left with mole, which is essentially the unit on the left hand side. Equal is a very, very powerful mathematical symbol. When you write equal, you need to make sure that it's really equal, and that is to do with following the units. Follow the units, especially in this topic from this point onward when we do mole calculation. Follow the units, write the units. Any units that you forget, then you can forget about doing well for stoichiometry and mole calculations. Follow the units. Mass over AR or mass over MR equal to mole. The mass is in gram, the AR or the MR is in gram per mole. I talk about AR because this is for the elements as governed or as given in the periodic table of the elements, but you also have MR. MR is relative molecular mass. As we did in the last lecture tutorial, you basically sum up all the relative atomic masses, and don't forget that relative formula mass can also be used to describe ionic compounds, which don't consist of atoms but instead consist of ions. It's just a different name. Both of them were calculated using the exact same method. Just sum up how many of the atoms you have, multiplied by the relative atomic mass as given in the periodic table. So now going back to these calculations, so they have given you an example here, empirical formula. So this kind of table is very, very important to set up. You don't need to write, you don't need to draw a table with all the lines, but you need to write very, very neatly on what you're trying to say really. Okay, so these are percentage. The sum of percentage is out of 100%. So sum of percentage, just like your exam marks, exam percentage is out of 100%. So this is mass per 100 gram. So typically I would label this mass per 100 gram. So that means out of 100 gram, how much is actually the mass of carbon in gram, the mass in gram. The stroke simply refers to in gram, is the unit, is a separation between the quantity and the unit. So the mass in gram of carbon is 12.8 gram, 2.1 gram, 85.1 gram. These are percentage mass composition. They can say percentage composition by mass. That is very, very important. Percentage composition by mass. Okay. Now, mole, these are atoms, by the way. These are atom, and atom. And the reason why they are atom is because of empirical formula definition. Is here, simplest whole number ratio of the atoms or the ions in a compound. Therefore, I do not divide by the by 2, which is the molecular mass for H2, but this is atom, so it's divided by the relative atomic mass for the atom. Okay, atom, carbon atom has a relative atomic mass of 12 as given in your periodic table, and then this one is 80. This is a relative atomic mass for bromine. Okay, so you got these things in decimal place, but you don't round them up straight away. You have to do this next step called simplest ratio. You divide by the smallest number throughout. The smallest number out of the mole calculation you had done, the smallest number is 1.06. So 1.06 over 1.06, which is itself is 1. This is very close to 1.06. When you put this into a calculator, you get 1.00 something, which is close to 1. 2.1 also divide by 1.06, and you get something which is close to 2. And do not forget that these are already whole number, and what do we have? Simplest whole number ratio. Okay, so it has to be whole number. So these are the whole number ratio. This is for carbon, hydrogen, and bromine atoms. So there's 1 carbon atom, 2 hydrogen atom, and bromine is 1 bromine atom. So the empirical formula, the simplest ratio of atoms, well, in the compound of the different atoms in this compound is CH2Br. So I think it's important that I probably go through a couple of these examples before I actually finish the tutorial, because otherwise the next part of these lecture tutorials on empirical and molecular formula will get too long. So let's get started. In this first question, we have this idea on magnesium combining with chlorine. They did not say chlorine molecule or chlorine gas, so we have to think very carefully about this. And they want the empirical formula for magnesium chloride. Okay, so I don't really like the way this question has phrased itself, but assuming that CO2 is actually how chlorine normally exists as, but remember that we are trying to find empirical formula. So even though this is for CO2 molecule, which is how it exists as, and magnesium exists as just Mg, giant metallic structure, simple molecular structure, but when you think about it, when you have this much mass of the molecule, then the mass of the molecule is exactly the same as the mass of the atoms, because the atoms come from the molecule itself. So the mass itself never changes, right? Because just because you're made out of 2 atoms, so the sum of the mass of each of these atoms add up to the mass of the molecule. So I'll be working with masses. So if I set up my table, Mg and Cl, I do not use Cl2 because of the definition of empirical formula, which is to do with the simplest whole number ratio of atoms or ions in a compound. Okay, so here I actually can think of it in terms of the atoms, but I know it is actually ionic compound. So I'll have the mass. The mass in gram is 0.96 gram. The mass in gram is 2.84 gram. So the mole will have a unit of mole. Mole is equal to the mass in gram divided by the relative atomic mass in gram per mole. So that is 0.96 divided by 24, straight from your periodic table. So read the relative atomic mass, do not read the proton number. So they give me 0.04. 2.84 over 35.5. Because it's the ratio, simplest whole number ratio of the atoms, I have to use relative atomic mass, never the relative molecular mass. Okay, so I get 0.08, and I then do my simplest whole number ratio. So simplest ratio, the smaller number is going to be 0.04, so I divide by the smaller number. So that divided by itself is 1. That divided by 0.04 give me 2. So these are the simplest whole number ratio. So therefore the empirical formula, which is again to do with the simplest whole number ratio of the atoms or the ions in a compound, okay? So it doesn't need to be one single molecule, because this is obviously a giant ionic structure which does not exist as a single molecule, and it does not matter because it's empirical formula. Molecular formula is the one that exists as single molecule, not empirical. On to question 2. So if I change the color of the ink here, so you have a compound of iron, and this compound contains this much mass of potassium. So if I have potassium, which is symbol K, iron, which is symbol Fe, and this is 0.195 gram, this is 0.547 gram. The whole reason of me not writing down the unit is because I have an entry where I write down the label of what I'm doing. Without label, this has no meaning. Without units, this has no meaning. But I write down the label and the unit. This is stroke gram, this means mass in gram, so I don't need to write down the unit again and again. Oops, before nitrogen I actually have carbon, so carbon and then nitrogen, so I have 0.252 gram of carbon and 0.294 gram of nitrogen, and I want the empirical formula of this compound, so I just work out the mole. So the mole is going to be mass over mR. Don't forget that the mass has a unit of gram and the mR has a unit of gram per mole. And it's not really mR, it's actually AR, because these are ratio of atoms, and AR is for single atoms from the periodic table. So mass in gram divided by the relative atomic mass. Let me just refer to my periodic table. So the AR of potassium is 39, and there is 0.195 for iron, that is divided by 56, there is 0.252 divided by 12, 0.294 divided by 14. So I'll pop all of that into your calculator. I get quite a nasty looking decimal thing, but I'll just run it up to 3 decimal place, or 2 significant figure. Perhaps 3 sig fig would have been alright, because all the data are given to 3 sig fig, 3 sig fig, 3 sig fig, and 3 significant figure. Significant figure is a primary school mathematics. Your data has to follow how many significant figure is given in the question, alright? Not based on what you think, but based on what is appropriate from the question. This one give me 0.00348. The next one, 0.252 divided by 12, give me 0.021. And the last one, 0.294 divided by 14, give me 0.021 as well. So out of all of these, the smallest one is actually this one, 0.00348. So what I can do is I can divide the whole thing, each and every entry, divide by 0.00348. So divide by 0.00348 throughout. So you should show your working. Unfortunately, I run out of space here. I should really show the working like this and this. I run out of space here, but you can do yourself. 0.0140 divided by that. I get 4.02. That's to 3 sig fig. And then this thing divided by itself, because it's the smallest number, give me 1 exactly. 0.021 divided by 0.021 divided by that, give me 6.03. And then 0.021 divided, well, give me the exact same thing actually. So these are very close to the whole number, so there isn't anything suspicious about it. I'll tell you the next time about what I mean by suspicious, but the nearest whole number is 4, 1, 6, and 6. So obviously we can think about the empirical formula being K4 FE1, which I don't show the one, C6 and 6. Alright, so this is not the end of these stuff that we have in the notes, and this is not the end of the lecture tutorial series actually, but I'll continue the rest of it in the next lecture tutorial. Otherwise, this will become a really long lecture tutorial. So hopefully give you some time to digest the concept and think about what we have gone through. Okay, so see you in the next lecture tutorial. Thank you for watching, and remember there's a part 2 to this as well, and do catch that when that get released, and subscribe to the channel. Click the button on the bottom right just to do that, as easy as that. And follow me at ptet.chemistry on Instagram, Facebook and Twitter. And yeah, thank you for watching.